Thank you very much, everyone. We're back. Let's take a look at, again, Physics 210. I want to finish out the course in kind of some kind of summary here. I'm going to try not to make the problems any more difficult than these problems are, at least for the upcoming exams. Final exam, we'll see exactly how I'm going to do the final exam, you guys. It's going to be online. It's going to be stuff you've seen. I have given you very, very many problems. You know that, to look at. I've not only given you problems because I'm a problematic person, I also tried to solve problems for you. Okay, so I hope it worked out for you guys a little bit. This is where I'm going to try to go and get through this, because we've got a lot going on, as you all already know now, this spring semester 2020. Physics 210, Chapter 33, problems 35, 39, 65. Then Chapter 34, problems 32 and 41. Chapter 35, problems 7 and 8. Chapter 37, problem 56. Chapter 38, problems 30, 55, and 61. But try to knock these out right now, guys. You're going to have to look in each one of these chapters at the relevant equations. I will, of course, bring them up while I'm solving the problem, but you're going to have to read these chapters over the next month, month and a half. Over the next month and a half, you've got to read these chapters, get some basic feel for what's going on. A lot of what's being said in there is not the easiest stuff to comprehend. I'm going to keep it at a relatively basic level, and I'm going to try to show you how to do this. So with all of that in mind, let's get down to some business. Chapter 33, 35, 39, 65. So let's look at 35, and we'll take it from there, guys. Let me go through. And there's a lot there. There's a lot more notes than I can go through, obviously. You guys know that. I know you're reasonable with me regarding that stuff, so and I'm going to try to be reasonable with you guys. So what is going on here? For 35, they're asking, problem number 35 in chapter 33. Number 35, an AC generator delivers an alternating current. I of t equals 2 amps times the sine of the quantity, 120 pi radians per second times t, to a single resistor in series with the generator. A, B, C, D. Here we go. A, what is the RMS value of the current in the circuit? If the resistor has a resistance of 100 ohms, what is the RMS value of the source EMF? What is the maximum value of the source EMF? Write a function that describes the source EMF as a function of time. Should go pretty straightforward, you guys. Alternating current goes back and forth. Back and forth current happens when you have the stuff that we had earlier. What was the stuff that we had earlier? We had a B field and we had a generator. And we had, what was the generator all about? Well, it had a wire that had a lot of coils in it, or maybe just one coil. Had perhaps a number of coils in it, and the wire was spinning perpendicular to the magnetic field. The area, the effective area being hit was changing, the flux was changing. A change in flux induced an electromotive force. It induced a potential difference. The induced potential difference induced a current, would make a current move. That induced EMF would constantly change because something was spinning around. Because of the spinning around of the generator, it wasn't the same EMF that was being generated, nor was the direction of the EMF the same as it was spinning around. The fact that the direction of the EMF was constantly changing and the value of the EMF was constantly changing, and the direction, as we said, that is indicative of an alternating current, a current going back and forth. And there's a lot of ways in which that can be generated. I just told you one of those ways. So what are they talking about here? So when they say something like this, I of t equals I and they gave us this mathematics. Let me take the units out of there and let's go here. That's what I is. RMS is the root mean square. The IRMS current is Imax, and again, the book's got all the relevant equations, guys. I have to ask you to read the book and at least be reading the last part of the book where they're telling you what they're trying to say. The book in general, read it and then read the summary at the end of each chapter, and that'll get us there. Otherwise, I'm not going to have time to finish all this. I am kind of pressed for time, guys. We don't know what's going on with the crisis that's going on here. So I've got to move at a good pace. I'm not trying to be obnoxious toward anyone. You guys know that. They told us it was 2 amps was the max. 2 amps divided by the square root of 2 is the square root of 2. Square root of 2 amps. What is that? Well, square root of 2 is 1.414. And there it is, that's A. B they're asking, so that's A. B, they're asking for the, that's for a bunch of stuff here. Let's see exactly what they're trying to say on that one. Let me get to it. Guys, forgive me here. The ERMS, okay, for some reason here, I don't think they should have, I may have written something I should not have written, guys. Let me just make sure I got it. I got a feeling it's right anyway, but let's make sure. If the resistor has a resistance of this much, what is the RMS value of the source EMF? Yeah, it should not be A right there. That's, I give an A for part B. It says A, it should be volts. I am just trying to put this together here. Let me see exactly what they're trying to say here. Right. What is the RMS value of the current in the circuit? If the resistor has a resistance, what is the RMS value of the source EMF? So I think this is not, my notes are not good right there. So take a note of that and just fix look what I'm fixing right now. Okay, a lot has happened here. So let me just tell you what you should be doing. Again, make sure you're watching this stuff. E is IR. ERMS is Emax over the square root of 2. Emax, see, I did something here I shouldn't have done, but that's okay. We're going to fix it right now, in fact. Emax is Imax times R, and over the square root of 2 is going to keep us going. This right here is the RRMS. IRMS. So this right there is IRMS. It's going to be Imax, which is 2 divided by the square root of 2, is this. That's what I just put in parentheses. The resistance is 100. And okay, I mean, I gave the numeric value right. I don't know where I got, I should not have said amps. I should have said volts. That's volts. Either somewhere I made a mistake, but this is correct. The numbers are right. I just put the wrong unit on there. I put amps initially, and it should have been volts. Okay. Be aware of that. You are looking at this. So, let's see what we got here, guys. All right, we're looking good there. That's B. Let's look at C. C, they're saying, what is Emax? It's pretty easy stuff, guys. What's Emax? Emax is going to be Imax times R is going to be 2 times 100. It's as simple as that. It's so simple. It's a little on the deceptive side. I guess kind of you might, it might take you in the wrong direction. You might be tempted to go in the wrong direction there on that. So that is what about D? D, they're saying, give me a general expression of what's going on. Wow, it's pretty straightforward stuff, guys. I mean, again, this looks a lot like what was going on with the flux, if you're really careful about it. So you got this. Okay, so what? Well, why don't you put an R in here? E would be I times R, would be I max times R times the sine omega t. All right, plug in all appropriate values, I guess you could say. This is 200, this is 100, that's 2. The whole thing is 200 times the sine of this, omega is 120 pi. At the end of the day, the mathematics is telling you 200 sine omega t. That's it. And I think that's it. I think that's for this one. That's indeed 35. 39. And again, guys, look at the book. I'm always kind of look at the stuff in relation to the book. Problem number 39. AC circuit with capacitance now. 39. An 8 microfarad capacitor is connected across an AC source with an RMS voltage of 68 volts. So an 8 microfarad, an 8 millifarad capacitor is connected across an AC source with an RMS voltage of 68 volts, oscillating with a frequency of 50 hertz. What are the capacitive reactance, B, the RMS current in, and maximum current, RMS current in and maximum current in this circuit? So this is the way they wrote this question is a little wacky, but we can do it. All right, so looking at 39, all right, you got to kind of look at a few things here, guys. They don't really aggravating about some of the notes in the back here, guys. I wish they put these things. It's just very strange. Okay, here we go. We got it kind of in the back of our mind doing a lot of this stuff, you guys. When we're looking at it, for 39, it's just some stuff you kind of keep in the back of your mind, I guess you could say. Omega is the frequency of oscillation of the current itself. It's a lot like what we did in Physics 209, mechanics, where a mass was oscillating back and forth. Well, the mass in this case is the current, if you will. So omega is 2 pi f, it works that way. And there's some fascinating conclusions that can be drawn. There is capacitive reactance that we are told about. Capacitive reactance, which is X sub C equals 1 over omega C. X sub C equals 1 over omega C. It's like a kind of resistance in a sense. It resists the flow back and forth of current. So it's okay, that's X sub C. That's capacitive reactance. Inductive reactance is omega L. And the impedance is the grand total
sort of resistance that occurs when all three of these guys are in series with one another. Doesn't matter which one you put first, XL or XC, because what happens is one's positive, one's negative a lot of times, but you square it, you get the same answer here. And the resistance is this. So this is playing the game quite a bit. I mean, this is where we're going with something like that. Some other equations will come into play as well, but let's look at this. Let's see what we can say regarding what they're trying to tell us here, guys. All right, guys. For 39, again, it's the way the question gets asked. An 8 millifarad capacitor is connected across an AC source with RMS voltage of 68 volts, oscillating with a frequency. The frequency F, that's F. Omega is 2 pi F. F is 50 hertz. What are A, the capacitive reactance, B, the RMS current in, and C, the maximum current in this circuit? So, okay, the way it got asked, should be pretty easy, guys. Should be pretty straightforward. So, with this right here, you got a capacitor. So how's the current, what's the potential difference across the capacitor and everything else? Well, they told us a lot. So let's talk about the a lot that they told us. You got 8. Okay. Well, they gave us this. We knew this. To talk about A, you're going to say that what is the capacitive reactance? You're going to go 1 over omega C, which is 1 over 2 pi F times C. C is the capacitance. That's 1 over 2 pi. F, they told us, is 50. The capacitance, is this. And you got this. At the end of the day, XC .398 ohms. It's in the same units, you guys, as resistance. And that's A. That's A. I will erase right over the, I'll erase right here. I'll take it from there. I'll continue. Let's keep setting this thing up, guys. We're talking. Sorry, guys, I have a hard time turning the pages here. There's just a capacitor there, so we're figuring out how this whole plays out with just the capacitor there. So you got 39. The IRMS is the same as the Imax divided by the square root of 2. The VCRMS is the same as the VC divided by the square root of 2. So when you got the RMS in there, you got to kind of keep it universally present, I guess you could say. This looks a lot like voltage divided by resistance. Voltage divided by resistance will give you current. This guy behaves like resistance. So voltage divided by something that behaves like resistance will give you the current. We are told 68 is the voltage. We calculated this already, just now. That is the IRMS. IRMS is 171 amps. Simple as that. That's B. C, what's I max? I max is a pretty easy move to make, guys. I max equals I RMS times the square root of 2. Why is that so? Well, it's so for a lot of reasons. I mean, I RMS multiply by the square root of 2 on each side, you get to here. If you take 171 and multiply it by the square root of 2, you get somewhere in the ballpark of 241.7 amps. $241.7 amps, not bad. That gets us through 39. Let's go to 65. For 65, and it gets a little tougher. In an RLC circuit, R is resistance, L is inductance, C is capacitance. In an RLC circuit, the resistance is 325 ohms, the inductance is 126 millihenries, and the capacitance is 13.7 millifarads. The angular frequency, that's omega. When they say frequency, it's F. When they say angular frequency, that's omega. The angular frequency is 377 radians per second. E max is 18.8 volts. A, what is the impedance? B, what is the maximum current? C, what is the phase constant phi of the power supply's EMF with respect to the current? So what is the phase constant phi of the power supply's EMF with respect to the current? Okay, that should be interesting. All right, we're going to look at a lot of the stuff that we're doing here. Let's get this, let's get it on the road. Let me erase this. So I'm going to erase everything I wrote except for that thing that says about where we are on that. All right, let's draw a couple things here. And let's just go down the line. Let's write down the data that we got, and I think we can make this make a lot of sense. We have got a power source, and they put a sine wave on it because it alternates, just like a sine wave alternates. This is a symbol for an inductor. This is a symbol for a resistor. Symbol for a capacitor. And that's your RCL circuit, or RLC circuit. That is L. That is R. That is C. And they gave us some data, and we're gonna run with it a little bit. R is 325 ohms. L is 126 millihenries. C is 13.7 millifarads. What does that mean? I mean, what means 13.7 times 10 to the negative 3 farads? What does millihenry mean? Well, it means 0.126. Millihenries is 126 times 10 to the negative 3, which is 0.126, or 126. You can write it like that, and this, of course, is what it is. I mean, we're not going to worry about that. It's just what it is. All right. When they get taken, when you're finding the associated capacitive reactance associated with C, or the inductive reactance associated with L, they have the same units as resistance. They have ohms. So we have this. We wrote this. And they told us a bunch of things here. They said 377 radians per second. That is the angular frequency is not the same as frequency. Angular frequency is not the same as frequency. So you got this. Emax, again, my notes here, they kind of got chewed up a little bit. So yours should be better on the computer. It should be 18.8 volts, I think it is. I just didn't write out too good. So there's a lot here. There's a lot of data here. Let's explore. Let's go. The total impedance is given by XL minus XC, the quantity XL minus XC squared, plus R squared, the sum of both those quantities square rooted. Will give you what the total impedance is. Well, I'll tell you what. There's a lot here. Let's be careful with it. Let me not give all the specifics of the actual numbers, but let me show you what you're going to do. You're going to the way this can get written now is you got to remember who's who. XL is omega L. XC is 1 over omega C. You're squaring that. And then you're squaring the R. So it's looking something like that. See what we got here. Well, let's put in all the numbers now. You know who's who. I already told you who L was. I already told you who C was. I already said who omega was. And we got this guy as R squared. Plug in a lot of the numbers, and then we're a lot of the way there, I guess you could say. The inside mumbo jumbo, the XL minus 1 over XC, the XL minus 1 over XC is 47.31. That's XL minus 1 over, forgive me, yeah, that's XL minus XC, which is the same as omega L minus 1 over omega C. And the resistance, they told us, is this. All right. Z is 328.425 ohms. 328.425 ohms. That's A. B. Imax is Emax over R. Well, yeah, it is if you're talking about R. I let myself slip a little bit. The new R, so to speak, is Z. Is the total impedance. Total impedance. So what do you got? You got 18.8 volts. They told me about that. The other thing was 328. Yeah, sounds good to me. There's a lot of ways you can write it. And again, you guys got the notes handy. 0.0572. All right, that's B. Forgive me here, let me just see here. That's that. That's B, okay, we wrote that. C, they're asking you what the phi is. What's the angle under consideration vis-a-vis the EMF and vis-a-vis the current. The current is going to be moving out of phase with what the generator is putting out. The resistance, the EMF and the resistance is in phase with the generator's EMF, but the current I is out of phase with that. By how much? Well, I'll tell you what I'm going to do. We could say that the tangent of phi is equal to XL minus XC over R. And phi is equal to the inverse tangent of the whole song and dance that was going on earlier. Well, we already did that whole song and dance. It was the 47.31, wasn't it? I mean, so we actually, you know, I wrote it out in a little more detail. But, the 47.308.4 over the resistance phi .28 degrees got that, got the other way, you know, either one's going to be fine on that. So what's going on there? I mean, the whole process is they work with the phasors. They're saying there is a voltage this way, there's a voltage that way, not necessarily the same size, and there's a voltage this way in a sense. And it's you know, the I is going to be the same in this series circuit, so it's going to be I, you know, going to be voltage associated with IXL, IXC, and IR. If I is the same, it cancels out of there, and you got the whole thing just reduces, and this thing's spinning around. I mean, so you got this, it reduces to R. You can just factor, you know, as far as the proportions are concerned, this is XL, this is XC. The voltage always shows up first and foremost with the inductor. The inductor exerts a voltage that tries to fight what's going on. After some charge gets on this capacitor, that's when it exerts voltage. But this guy exerts voltage right off the bat. And this is in phase with the generator. So if you subtract the two, if you subtract these two, do kind of like a vector sum, this is what they're talking about. And that's Z. I times Z is the way the current's actually moving, and this is the generator's voltage, and this is phi. They're going along those lines. Again, guys, this is where I wish I had you guys for at least a month or two, which I don't get to have. So I'm just kind of throwing this at you, and just read the stuff and look at it. And we can do what we can do. Let's see whether there's something else on this. No, it wasn't. It took us all the way through. In fact, that took us through chapter 33. At least what I wanted to say now, at least in a rudimentary form, for you guys to kind of have in your mind here. So what is the phase constant for C? C was, what is the phase constant phi of the power supply's EMF with respect to the current? And we just said it. So that's pretty neat. That's pretty neat stuff how that works out. So there's some other really, really great problems here that have been done. I mean, 73 and 82. 73 and 82 are really good. I've got them in the notes. Might want to look at them. I wish I had time to do them, guys. The way we got caught, you know what I mean, is the way we got caught. So let's go go to chapter 34, problems 32 and 41, if that's okay. So I'm going to erase all this. Just look at this very, very quickly, guys, just to kind of get an idea of what's happening here, right? Absolutely, yeah, looks very good. So the whole process, guys, when you're doing this, yeah, it looks good, it looks good. It looks good enough. For what we want to say right now, it looks good, guys. There's so much more that truly would need to be said regarding that, but we're okay right now. So let's keep going.